Okay, good morning students. So, the continuation of the last class, how to design a FIR filter. So, generally with the system function, what is a FIR filter, what is a IR filter we have described. So, now we will start with the practical the magnitude characteristics of frequency selective filters. Generally the is a magnitude characteristics. Magnitude characteristics okay, frequency selective filters. Filters. So, this is the actually if you see the ideal characteristics of the filters, this is the ideal characteristics. Okay. But practically you will not get the ideal one, only you will get the approximation, you can closer to the approximation. So, this is your pass band, this is your stop band. Okay. So, as I said, the practically will not be like this. So, you can closer to the, that is the approximation. So, this is a magnitude response h of omega. We will see the magnitude characteristics of frequency filters. So, this is your pass band. If you see here, no, this is your pass band, this is your pass band, pass band. Okay. This is your this is your stop band, stop band. So, this is your transition band, transition band. Okay. Transition band. So, there will be a ripples in the pass band, this is ripples in the pass band 1 plus del 1 and 1 minus del 1, okay, minus del 1, this is a ripples in the pass band. So, this is the ripples in the stop band del 2. So, del 1 ripples in the pass band, ripples in the pass band, del 2 ripples in the stop band. So, this is omega b, this is omega s. Okay. This is a pass band H frequency, pass band H frequency, frequency, stop, this is the stop band H frequency. Okay, this is a magnitude characteristics of the frequency selective filters. Although the frequency response for the ideal filters may be desirable, in most practical applications, okay, you can get only the approximation, okay, which is closer to the desired frequency response. So, it is not necessary that the magnitude, it is not necessary the magnitude h of omega be constant in the entire pass band. A small amount of ripples in the pass band, which is usually tolerable one. Similarly, it is not necessary for the filter response to be 0 in the stop band. A small non-zero value or a small amount of ripples in the stop band is also tolerable. So, the transition of the frequency response from the pass band to the stop band defines the transition band. So, the transition from the pass band to stop band defines the transition band. The pass band edge frequency omega p defines the edge of the pass band. The Ws denotes the beginning of the stop band. So, the width of the omega s minus omega p, the width of the omega s minus omega p is called transition band. So, the width of the pass band, the width of the pass band is usually called bandwidth. The width of the pass band is usually called the bandwidth of the filter. So, the ripples denotes del 1, okay, and the magnitude Hd of omega desired frequency response varies between the limits 1 plus or minus del 1, 1 plus or minus del 1, 1 plus del 1 and 1 minus del 1 ripples in the pass band. Similarly, the ripples in the stop band is denoted by del 2, ripples in the stop band is denoted by the del 2. So, normally to accommodate a large dynamic range for the frequency response of any filter, normally in common practice we use the logarithmic scale, okay, logarithmic scale. So, del 1 you can take 20 log del 1 decibels, similarly del 2 you can take 20 log del 2 decibels. So, in any filter design, the maximum tolerable pass band ripple, maximum tolerable stop band ripple, pass band edge frequency, stop band edge frequency. So, based on these frequencies, these specifications, we can select the parameters, the coefficients we are seeing the system function, no, AK and BK. So, AK, BK coefficients on the system, the BK coefficients and AK coefficients zeros, the numerator polynomial coefficients BK, the denominator polynomial coefficients AK in the frequency response which approximates by selecting these parameters, okay, in the frequency response characteristics which approximates the desired specification. Okay. So, this is the basic FIR filter magnitude characteristics of frequency selective filters. Okay. Next we will see FIR, the symmetric and antisymmetric condition for FIR filters. Okay. Symmetry and antisymmetric FIR filters. So, we know that the already FIR filter, how it can be described by the difference equation. Okay, what is the equation? So, the difference equation, any FIR, so FIR filter with the finite sequence length m with input x of n and output y of n can be described by the difference equation y of n, which is equal to b naught x of n plus b 1 x of n minus 1 plus b m minus 1 x of n minus m plus 1. So, we can write y of n is equal to summation of k equal to 0 to m minus 1 b k into x of n minus k. So, you know convolution also, as we discussed, this is h of k in the convolution, it is h of k, okay, into z minus k. So, h of z for the FIR filter you can write summation of k equal to 0 to m minus 1 h of k into z power minus k. So, the polynomial of degree m minus 1 in the variable z inverse. So, the roots of the polynomial coefficients, are the zeros of the system. So, FIR filter has linear phase FIR filter. Okay, so, the condition h of n is equal to plus or minus h of m minus 1 minus n. Okay, where n is equal to 0, 1 up to m minus 1. So, when this symmetric plus symmetric and antisymmetric conditions are applied in this equation, for example, this equation second, this equation may be 1. If you incorporate this symmetric and antisymmetric condition in this equation, you can write the system function h of z, which is equal to h of 0 plus h of 1 into z inverse plus h of 2 into z minus 2 plus h of m minus 1 into z power minus m minus 1. Okay. If you see, so the symmetric condition, for example, m is equal to 8 you will take. So, what is the symmetric condition? H of n is equal to h of m minus 1 minus n. So, h of, for example, 8 minus 1 minus n. So, which is equal to h of 7 minus n. So, if you substitute n equal to 0, then h of 0 will be h of 7, is it? Similarly, if n is equal to 1, h of 1 will be h of 7 minus 1, 6. Similarly, h of n is equal to 2, h of 2 will be h of 5. If n is equal to 3, h of 3 will be h of 4. If n is equal to 5 means h of 5 will be h of 3. If n is equal to 6 means h of 6 will be h of 1. If n is equal to 7 means h of 7 will be h of 0. So, with respect to symmetry and antisymmetry condition, we can classify the system function for m is equal to odd and m is equal to even. So, the m may be odd or the m may be even. For m is equal to odd and m is equal to even, we can write the magnitude response for symmetric and antisymmetric. The magnitude response HR and the phase. The magnitude and phase you can write for this symmetric and antisymmetric for m is equal to odd and m is equal to even. So, all these equations should remember. So, that here if you notify, if you substitute z inverse and you can multiply both sides by z minus m minus 1, you can write this also, you can say z inverse of m minus 1 h of z inverse equal to plus or minus h of z also. So, this results implies that the roots of the polynomial h of z are identical to the roots of the polynomial h of z inverse. In other words, you can say if z1 is a root or 0 of x of z, 1 by z also. If z is a root of, if for example, if z1 is a root or 0 of h of z, then 1 by z1 also a root. That is the condition for this one. So, for example, for symmetry condition, I will write the expression this video when when h of n is equal to symmetric, means h of m minus 1 minus n. Now you can write h of omega, the magnitude response will be h of omega can be written as real term hr of omega into e power minus j omega alpha is equal to m minus 1 by 2. Okay. So, this hr of omega is a real function, it is a real function of omega, and it can be expressed as hr of omega which is equal to h of m minus 1 by 2 plus 2 the summation of n equal to 0 m minus 3 by 2 h of n into cosine function cos of m minus 1 by 2 minus n for m is equal to odd, okay, which is equal to h of m minus 1 by 2 plus sorry, not this one, okay, this is for m is equal to odd. For m is equal to even, this hr of omega, okay, real function is equal to 2 into the summation of n equal to 0 to m by 2 minus 1 h of n cos omega m minus 1 by 2 minus n in n. This is for m is equal to even. For both the phase is equal to, the phase will be theta of omega is same for both m is equal to odd and even. So, which is minus w m minus 1 by 2 if hr of omega is greater than 0 and minus omega of m minus 1 by 2 plus pi if hr of omega is less than 0. Okay, this is for symmetry condition. See, if when h of n is equal to plus, this is plus symmetric, this is symmetry condition. Symmetry condition. Otherwise we can silent here. H of n is equal to h of m minus 1 minus n. It is a symmetric. You can write the real function of omega is equal to h of m minus 1 by 2 plus 2 summation of n equal to 0 to m minus 3 by 2 h of n cos m minus 1 by 2 minus n for m odd, and another real function if m is equal to even. The phase characteristics, this is a phase characteristics, this is a phase characteristics. The phase characteristic is the filter for both m odd and even is minus w of m minus 1 by 2 if a real function is greater than 0, and for real function is less than 0 plus pi. Similarly, when it is an antisymmetric condition, what is the antisymmetric condition? Okay, for antisymmetric condition, what is it? H of n is equal to minus h of m minus 1 minus n. So, this is the unit sample response is antisymmetric. This is the antisymmetric condition. This unit sample response is antisymmetric. Antisymmetric minus sign. So, for m is equal to odd What about the center point? So, for m is equal to odd, if m is equal to odd, okay, the center point for the antisymmetric will be, the center point will be n is equal to m minus 1 by 2. So, consequently h of m minus 1 by 2 equal to 0. But if m is even, if m is equal to even term, okay, then each term will be the for each h of n has a matching term of opposite sign. So, if the frequency response of the filter is antisymmetric, then the h of omega can be the magnitude response, the frequency response can be expressed as hr of omega into e power j, okay, minus omega of m minus 1 by 2 plus pi by 2, where the real time hr of omega is equal to 2 summation of n equal to 0 to m minus 3 by 2 h of n sin omega of m minus 1 by 2 minus n if m is equal to odd. Similarly, this hr of the real time function 2 into the summation of n equal to 0 to m by 2 minus 1 h of n sin omega m minus 1 by 2 minus n for m is equal to even. The phase characteristics of the for both m equal to odd and even will be the theta of omega is equal to pi by 2 minus w m minus 1 by 2 if hr of omega is greater than 0, 3 pi by 2 minus omega into m minus 1 by 2 if hr of omega is less than 0. So, these general frequency response formulas, all these formulas can be used to design linear phase FIR filters with symmetric and antisymmetric conditions. Note down for symmetric h of n, here I symmetric h of n. So, note for symmetric h of n, the number of filter coefficients for symmetric h of n, for symmetric h of n, the number of filter coefficients, the number of filter coefficients, the number of filter coefficients is m plus 1 by 2 for m is equal to odd and m by 2 if m is equal to even. So, note down symmetric h of n m plus m is equal to odd. If it is a symmetric function, the filter coefficients will be m plus 1 by 2, and if m is even, then m by 2 filter coefficients. So, remember that. On the other hand, if it is antisymmetric, Okay, if it is an antisymmetric, if it is an antisymmetric condition, then for m is equal to the filter coefficients for m is equal to odd and m is equal to even. In that case, for antisymmetric, the number of filter coefficients will be the number of filter coefficients okay, m minus 1 by 2 for m is odd and m by 2 coefficients for m is equal to even. So, depending upon the application, the choice of symmetric or antisymmetric unit sample response you can take. Clear? So, normally we will not use antisymmetric condition in the design of low pass linear phase FIR filter. On the other hand, the symmetric condition h of n is equal to h of m minus 1 minus n, the symmetric condition. What is the symmetric condition actually? H of n is equal to h of m minus 1 minus n yields a linear phase, which is a linear phase FIR filter with a non-zero response at omega equals 0. So, to design a FIR filter, it is simply to determine the m coefficients h of n is h of n equal to 0 to 0 1 up to m minus 1 from a specification of the desired frequency response of the FIR filter. Okay. So, with this we can complete the session. The next session we will discuss about the FIR filter design using window method. Okay. So, why we go for window method we will discuss in the next session. So, the first session we discuss about the DT systems, how to implement the DT systems using Z transform, how the Z transform system functions are described by the numerator polynomial coefficients by the denominator polynomial coefficients. The numerator polynomial coefficients are called FIR filter. So, that is the zeros of the system, it has a finite impulse response coefficients, and how the FIR is called a linear phase FIR filter, the magnitude, because the phase is a linear function of omega and it is more stable filter. So, FIR is a causal system, and how to describe the difference equation in terms of Z transform, and how the convolutional function minus symmetry plus symmetry is limited to 0 to m minus 1 for the FIR filters, how the impulse coefficients h of n is replaced with the coefficients bk coefficients. And second video we have discussed about the ideal desired frequency response characteristics for low pass filter, high pass filter, band pass filter, band stop filter. Then what is the magnitude characteristics of ideal in this video, what is the magnitude characteristics of ideal filter, frequency selective filter. The ideal one, we cannot get the ideal one, we can approximate the closer, we can closer to the ideal one. So, what are the tolerable ripples in the pass band and stop band? So, the bandwidth is a pass band frequency, and what is the parameters, different parameters, according to the different parameters specifications we can design the FIR filter. And in this FIR filter, if it is the impulse response h of n can be a symmetric or antisymmetric condition for symmetric and antisymmetric condition. So, if you see here actually in the filter, what are the three elements plays a vital role. If you see here, one is the summer and the multiplier and the unit delay element. If you see the realization, finally we can realize the filter h of 0. So, this is the summer, this is the delay element unit. The three elements of the filter designs are adder, okay, adder and multiplier and the unit delay element. The unit delay element is Z inverse. Unit delay element. How you can realize the finally the realization. After that the realization you have to direct realization we can do. So, h of n, this is a multiplier, this is the unit delay element, this is the adder element. The convolution. So, what are the three elements are involved in the convolution? The convolution function, summer, multiplier and delay element, the three. So, in the next year you will study in a design of FIR filter or IR filter, how to design efficient adder, how to design efficient multiplier by using VLSI technology, how to design a best adder, how to design a multiplier in order to optimize the design to meet area, less area, speed, high speed, okay, high speed, less area and power, low power. So, these are the VLSI. So, integration VLSI integrated circuits. Okay, next semester we will study in VLSI design, IC design. Okay. So, with high speed, low power, the minimized area, how to design an efficient adder multiplier. So, because this FIR filter design requires the three important, because when you these are the mathematical background and how to design a particular pass band or band pass filter or low pass filter, high pass filter. Finally, the realization hardware realization with respect to this optimization parameters. Okay, that okay. Next session we will discuss about the FIR design using window method. Thank you.